This is a recap of the discussion today that came out of number 28 in section 1.2 of the book, and that was a question relating, asking what about the pivots. So that was for a particular augmented matrix. What must be true about the pivots if we know that the equation, the system, let's say, the system is consistent, that is, a solution exists, that's an existence condition, and has a unique solution as well, so existence and uniqueness. And there was an important issue that I started talking about once the discussion started going, which is there's two kinds of results. The first one is if we're looking at the REF, the reduced row echelon form of the matrix, what can we say? And the answer is usually a lot. That's what it's for. But we need to know exactly what we can say there. And the important thing here is that this means we know, so in this case, we know exactly how many pivots there are and where are they. Okay. And then the second kind of result we'd like to look for, or I could say two kinds of questions, really. Maybe this is like two kinds of questions. The second is that if we're just looking at the original form of the system, assuming that it's not already magically or luckily in REF form, what can we say without any calculation? Are there any general theorems that we can say without any calculation? Okay, and well, what can we even observe out of that? We don't know. We can't say definite things about the pivots if we're in this second situation, but we can clearly count the rows and columns. Okay, so we then, to be more definite, we say, let's say that the augmented matrix has m rows, which is our standard letter for rows, and n plus 1 columns, so that there are n variables total. Okay. So just so we can be definite and abbreviate number of rows by number of equations, in other words, by m, and number of variables by n. Okay, and then of course there's one extra column for the right-hand side. Okay, so in for the answer for number 28, that was something about what can we say about pivots. And can we relate that, for example, to the rows and columns? And we figured out that the number of pivots has to be equal to n, which is the number of variables. Why was that? It certainly can't be bigger. We can't have number of pivots be bigger than the number of variables. Well, what would that mean? The only other place that a pivot could appear is in the far right-hand side, and that we know that means that there's no solution there. Okay, so that's for a fairly simple reason. The number of pivots can't be bigger than the number of variables, because otherwise it wouldn't even make sense, or we'd have to have a pivot in the last column and not have consistency. But we also can't have, the more interesting thing is the number of pivots can't be less than the number of variables, because that would imply having a free variable. And we're supposed to assume that if we know it has a unique solution. Okay. So that's why we concluded that the number of pivots must be equal to the number of columns of the coefficient part of the matrix, or in other words, n, or the number of variables. Okay. And was there a connection between, what about number of pivots and number of rows? And we couldn't be as definite about that because we could end up with the REF form could have some number of 0 rows. Okay. So we've got one relationship between pivots and variables, not any obvious relationship between pivots and rows, except, of course, that the number of pivots has to be less than or equal to the number of rows, which is m. Okay. Because it wouldn't make sense to have more pivots than rows. You're going to have at most one pivot in every row. Okay. So this is great information. It's really good to know this. But it is of the form, the question type number 1, that it explicitly talks about counting pivots, and we can't do that unless we've already got the REF form, or at least the row echelon form, maybe not all the way reduced. Okay. But can we say anything about maybe just rows and columns? Those are things we can, that's question type number 2, where stuff we can observe easily out of the original matrix itself. Okay. Well, we can conclude that we must have m at least as big. Where's my greater than or equal to? At least as big as n, just by combining these two results. We know that the number of pivots is less than or equal to the number of rows, but we know in this case, that's always true, but we know in this case where we have a unique solution that that number of pivots is equal to the number of variables. So we can connect these, the m and the n, which are easily accessible quantities, through the number of pivots, which is a harder to access quantity. So it's pretty cool. We don't even have to calculate the REF and get the pivots to use the pivot concept to conclude something. We must have m greater than or equal to n in this case where we get uniqueness, again, because otherwise we would get a free variable. But it's important to know that the reduced echelon form theorem, the fact that we can put it in reduced echelon form, we know how to sort of eliminate redundancy, which is another word. This is sort of systematically eliminating redundancy. That redundancy can be very, very subtle in a matrix before we reduce it. And it's nice that that eliminating redundancy idea corresponds directly to the REF form. That is something that actually tells us something about what shape this matrix must have. Okay, so for example, if we look at this matrix, there's 3 equations and 4 unknowns, and then here's the right-hand side. So if this is the augmented matrix, we can just look at this and say there's no possible way we could get a unique solution. Now I'm just going to go ahead and use the computer to do this, and now here's the row echelon form where we can see exactly what those solutions would be. What we can see is there's 3 pivot columns, and then here's a column with no pivot in it. And so the free x4 will be a free variable here, and then x3 will be determined in terms of this equation, x2 by this equation, x1 by this equation, but we will definitely have a free variable. Okay, so what about, I don't need to delete that. What about this matrix? Here, it's a 4 by 4. The coefficient part, everything but the left right-hand column, is 4 by 4. You might think, okay, this is going to be a nicer case where we're going to have, it looks like the number of equations is the number of variables. We ought to get a unique solution. Well, let's REF this guy. Uh-oh. Pivot column, pivot column, pivot column. No pivot in this column. And of course a row of zeros, because if there's only 3 pivots, then there's going to be a row of zeros if there's 4 rows. What's going on here is that, oh, and is it consistent? Yeah, it is consistent, but the answer is not unique. And you'll notice that it's very, very similar to what I had here. The answers are basically the same. The reason for that is what I did when I put this row in, it is redundant with the other rows. It's the sum of the other 3. And so this equation is a consequence of the other 3 equations. Now, that's a little subtle, and it's not easy to see right off the bat. And certainly if it were some more complicated linear combination of the other equations, it would be almost impossible to see directly. And so that's a subtle issue. So that tells us that we probably can't go beyond this statement in this case. Just saying, okay, if we know we have a unique solution, then we know that there must be m greater than or equal to n, but we can't go further and say, well, I think actually m must be equal to n, or if m equals n, then we definitely get uniqueness or something like that. Okay, so then where we went from this, I couldn't resist, even though this goes a little further, is here's a new question. What if we have a given coefficient matrix so that the system is consistent and has a unique solution for all right-hand sides. And so now, no matter what I do to the right-hand sides, I should be able to get a solution. Now, this one, let's go back to here. This one gave a solution, but it's extremely sensitive. This guy has to be a 5, because this left-hand side is the sum of these left-hand sides. This guy has to be the sum of these guys. If I change that to any other number, then I get a pivot in the right-hand column, and I'm stuck. I'm not going to get existence. And so that shows you that this situation, this weird situation where I put the sum of the 3 left-hand sides as the 4th left-hand side, is rather unstable. And so it's a much stronger condition. This is a much stronger condition. Okay. And that's the interesting situation we got to at the end. I don't want to make this video too long, but the claim we came to, and we'll come back to this again because this is really getting a little bit ahead of ourselves, is that in this situation we need to have m, which is the number of rows, is going to be equal to the number of pivots, which might be hard to figure out because you need the reduced echelon form, but the claim is that's also equal to n, the number of variables. And in particular, we must need m equals n. In other words, so the coefficient matrix must be square. And we really quickly ran through why in this situation that must be true, but I want you to think about that a little bit more, about why in this situation we actually get this very strong condition. Now, warning, okay, this is not an if and only if. Okay, just because you have a square matrix doesn't mean you will get consistency and uniqueness for all right-hand sides, and this is an example down here. Here's a square coefficient matrix. Here's a right-hand side that didn't work. And so that's still very important to realize. Okay.